Okay, binary coded decimals. Binary coded decimals are yet another way of encoding information into binary. So unlike binary or decimals, this is not a number base. So this is not base 2, this is not base 10. Binary coded decimals are sort of like a hybrid in between the two. All right, so let's see what we mean by that. Is that you're not actually encoding a number base. What you're encoding is base 10, but using binary, right? So I know it's a little bit confusing, so let's try and figure out exactly what it does. So a BCD is a 4-digit or 4-bit binary code that is used to represent a decimal digit, okay? So look at this table here. You have decimal values 0 through 9, so decimal means there's 10, and each one of those has a corresponding BCD that takes 4 bits. So you might say, well, isn't this, we've seen this before. This is just regular binary. Well, it is up to a point. So what I want you to focus on is now that each decimal digit, it has 4-bit code, look at this example, 923. The way it's encoded is that you take a 9, you take a 2, and you take a 3, right? It's made of 3 decimal digits. And the way it's encoded is each one of these decimal digits gets encoded as 4-bit binary. And then you concatenate and you're done. So this is in between a decimal and a binary. So what do we have here? Is that, let's just say 157. Instead of having to divide by 2 or whatever the number base is, in order to convert this, literally, it's just look up the table. 7 is 0, 1, 1, 1. 5 is 0, 1, 0, 1. And 1 is 0, 0, 0, 1. And you put it all together, and this is your BCD for 157. All right? So in a nutshell, that's what BCD is. It doesn't take it's not a number base. All it's doing is looking at a decimal number, and it's encoding each digit of that decimal number. All right? So let's take a look at some of the other properties of BCD. First is a BCD uses 4 bits, right? So remember that we're a computer science class. So especially hardware architecture. So we want to not just know how things are encoded, but we need to be aware that there's space limitations, right? We covered that during one of the prior classes to talk about overflow. So another thing about data storage is that data is stored in bytes. A byte is 8 bits. So if you have 8 bits, but its BCD is 4 bits, then one way of encoding it is using an uncompressed method, which means that looking at this example, if I want to encode the value 25, the way it could be encoded is I have 1 byte for 2 and 1 byte for 5, right? So here's where 2 is. Here's the 4-bit for 2, and here is the 4-bit for 5. Notice that put this in green, the preceding 4 bits are always zeros, padded with zeros. So when we have that, you end up with sort of wasted space, right? Even though you have 8 bits, only 4 of the bits are used. So this, I would argue, is inefficient storage, but however, the benefit is I can get each BCD very quickly, right? The first byte has a 2, the second one has a 5. I very quickly I go and just grab the individual BCDs. Now let's compare that to another method called packed. A packed method will put 2 BCD numbers into a single byte. So just like our prior example, we have 25. Notice that 2 is here and 5 is here. So it puts 2 BCDs per byte. So notice that very immediately comparing that to the byte pattern above, it uses half the amount of space because there's no wasted space. However, the downside is in order to retrieve 25, I have to know that the first 4 bits is 2 and the second 4 bits is 5. So it requires one extra level of parsing, right? Because the values are not always in the same place. It can be in the first 4 bits, or in the last 4 bits. So that is a trade-off or a compromise that you're going to see a lot when we talk about storage, especially in memory, in the sense that the choice is speed versus storage. That's going to be a common theme or a common trade-off you're going to see a lot of. Speed usually means you just write it quickly, retrieve it quickly. That's all we care about. But it doesn't necessarily store it in the most efficient manner. Okay, if you look at the bottom, it's stored in the most efficient manner because we have no wasted space. But to retrieve the data, you have that one extra step of retrieving the byte, and when the byte, locating either to the first 4 bits or the last 4 bits. So you have one extra step involved. This is a concept that you're going to see a lot of even when we talk about things like compression, where data can be retrieved very quickly, or if it's compressed, you have to decompress the data first before accessing it, which adds that overhead. So again, the trade-off is I can store things uncompressed very quick, and that means quick write, quick retrieve, but however, the possibility is I might waste space, or the other alternative is I minimize the waste of space, try to make it as efficient as possible, but then by doing so, I make retrieval and writing to it a little bit more expensive. Okay, all right, moving on. BCDs also support integers in the sense of signs like positive and negative. However, just like your ints or integers that we talked about, there's no sign for plus or positive or negative. So you can't just use 0 and 1 because BCDs are 4 bits. So to address a situation where we need a value to represent positive or negative, these are the 6 unused BCD values, right? Because we only needed to represent values 0 through 9. So A, B, C, D, E, F in hex, these values are technically not used in unsigned BCD. So because of that, if we want to use signed BCD, there's going to be 2 values that are going to be used for positive and negative, C and D. A good way of remembering this is positive is C for credit. So think about if someone credits your account, they're adding money, right? So think of that as positive. And if someone debits an account, they're actually removing. So think of it as negative. All right. So the hex value C, or the BCD for C, is 1100, and that's positive, and D is used for negative, and it's 1101. Now, another difference with BCDs and one of the other encodings is that the sign isn't placed to the left, it's placed to the right at the end of the number. Notice this example, negative 327 is stored as 3, 2, 7, and 1101 is D. And that corresponds to the value negative 327. Okay, so very important is that the C and D are used for positive, negative, and they are placed at the end of the number, not at the beginning. Okay, so with that said, give you guys your first exercise of the night. So here, there are 3 numbers. I want you to tell me which values are stored there if they were stored as BCDs. So tell me which values are there, all right? Okay, so let's do the first one. The first is 7, 2, and 110 is C. So this is positive 72. The next number is 2, and 010 is 5, and 1101 is D. So this is negative 25. And the last number is 72. There's no sign involved because there's no C or D at the end. Okay, so those are your three numbers. All right, let's take a look at the next thing.
Professor, would number 3 be just considered positive as a default?
Well, no, there's no sign bit, is there? So we're asking what's represented in it. So there's no sign bit, so leave it out.
So it's just a neither.
Remember, again, this is not a math class, right? This is a computer science class. So is there a representation of sign on number 3?
No, but it's confusing that there would be.
Well, no, it's not confusing. Again, think about this again. This is not a math class. This is a computer science class. So you're asked what's encoded there. You see the value 7 and you see a value 2. Do you see any representation for sign?
No.
No, then you leave the sign out. Whereas if you look at the first problem, they actually have an explicit representation of sign. So you're saying what is encoded there? It's positive. Okay.
So it's neither positive nor negative. It's just
correct. 72. Yeah.
72. Okay.
All right. You got that? It's not that hard when you think about, pretend you're a computer, right? We're asking, is there a sign encoded there? The answer is no.
I follow you.
All right. No problem. Okay. So next is, let's look at the range of numbers that can be represented using BCD. So we're using a 32-bit BCD, and let's take a look at the largest number. All right, so the largest number of BCD is going to be, well, let's try to work on this together. Each BCD is how many bits, guys? Let's see if you're going to pay attention all evening. How many bits is a BCD?
4.
4. Okay. So if each BCD has 4 bits, given 32 bits, how many BCDs can you represent using 32 bits?
8.
8. Okay. So we have 1, 2, 3, 4, 5, 6, 7, 8. All right. So I have 8 BCDs values. So the range of each BCD digit is what? 0 through 9, right? So what's the largest value at each position?
9.
9. Okay. So when everything is set to 9, your largest value is 99,999,000. So let's just round it up, add 1 to it. So this is approximately 100 million, correct? So the largest value is, you can represent 0 through 100 million. All right, so 2's complement has positive and negative, but just for comparison's purposes, let's just make everything positive. So with an integer, you can represent 4, the largest number is roughly 4 billion. Okay, so 4 billion is equal to 4,000 million. So we're talking about 40 times less, like 40 times less space. So given BCD, it's not very efficient in the sense that it can't, given the same number of bits, you can't represent as equal number of values because there's wasted space. Okay. All right, let's take another thing about BCDs. Fractions. We talked about floating point in the last class, where the part of the encoding for a floating point was that you had an exponent that told you where to put the decimal point, right? So BCDs do not have a floating point. However, you can implement what's called a implied fixed point. Okay, fixed point means that the decimal point doesn't move. And and there's, off the top of my head, there's only really one application where the decimal point is always in the same place. And that has to do with money, right? Think about it, dollars and cents. Everything is always going to be 2 decimal places over to represent cents. You're never going to have like .157 cents, right? It's always going to be 2 decimal places. So that's a perfect example of a fixed point. where the decimal point is always in the same place. So because of that, you can do what's called an implied fixed point, because there's no decimal point, or there's no representation for the decimal point inside BCD. So if you have a fixed point that's always in the same place, then just like we talked about the hidden one, when we talked about floats, it's sort of like when you encode this, the program who stores this information can say, okay, I am always going to put a decimal point in the same place, 2 points over, and it's going to be there. However, you're not going to see inside code because it's implied to be there. All right, so let me show you what I mean. So if we have this number, this example, negative 32.5, right, it can be encoded as negative 32.5 or 325, because they're both essentially encoded the exact same way. So how would we imply or encode an implied fixed point? So let's just quickly show you. So let's just do the value 173. Okay, and 17.3, and then $1.73. So the way to do it is implement the implied fixed point by changing this to 173.00, 17.30, and this is 1.73. So does everyone agree that the values on the left and the value on the right are the same value? They look different representation, but they're the same value, right? 17.3 is the same as 17.30. 173 is the same as 173.00. Everyone agree? So what you're doing here is aligning it just so that the decimal point is right there, okay? And once I have that, then the encoding is 1, 7, 3, 0, 0, right? So that's 17300. And now for this one, it would be, let's see, 0001, 0111, 0011, 0000. And the last one would be 0001, 0111, 0011. Notice that my implied fixed point would be around right here, but I don't need to put a decimal point because the way I recoded these numbers is that there's always 2 digits to the right of the decimal point. That's what I mean by a fixed point. Implied fixed point is I don't need to encode it because it's always implied to be there because of the way I shifted things around to always have 2 decimal places. Does that make sense, everybody? Okay, so let's quickly go do an exercise. And here we have 3 examples. So encode 25 into BCD, 2.5 into BCD, and 0.25. So pad it with, assuming that I'm trying to have an implied fixed point of 2 decimal places, change this binary code or BCD code to reflect how this would be encoded. Okay, so let's do this together. The first number, if I want to encode it with an implied fixed point, would be 0. Oh, actually, just do 0, 0, 0, 0, 0, right? Pad it with 2 zeros. So this would be 25.00. Okay. The next one I need to rewrite is 2.50. So I just need to pad it with 2 zeros. And the last one I don't need to do anything to because I can just keep it as is because already the last 2 decimal places. All right. Any questions on this one, on fractions? All right, moving on. Okay, so why BCD? Is that we already have binary, we already have decimal. So what's the advantage of using BCD? And really the main benefit comes down to the quick, easy translation of a decimal value from binary. So typically, this is historically, not typically, historically, this was used by small systems like clocks, right? Because when you have time, it's like 1201, 1202, 1203. You sort of don't need to do a lot of calculations. You just need to store the value that's going to be displayed. So with that being said, let's see how quick it is to convert from binary, which is how it's stored in the machine, and how quickly it gets translated for something to be displayed. So for example, 234, right? This can be translated quickly because each one of the digits, 2, 3, and 4, have a 1-to-1 relationship with the numerals and the BCD. So what am I talking about when I say 1-to-1 relationship? It's this. No calculations necessary. If I don't know what 215 is, I look at 2, it's 0010. 1 is 001, and 5 is 0101. Notice that no calculations involved, no addition, no subtraction, no division. Literally, it's just lookup. 4 bits, translate into a decimal. So that's the main advantage of BCD, is how quickly you can convert from decimal to BCD. So BCD, remember, if you look at it, zeros and ones, that's binary. It's how quickly you convert from a binary encoding into decimal. That's a main advantage of it, okay? Let's see, what else? So if we were to, let's just say, encode 234 into 2's complement, right? In order to get that value, you would have to do the number bases, right? Like 2 plus 8 plus 64 plus. So you would not only need to convert it, but then you had to do addition. So it just takes longer. So the other benefit is fractions, okay? So let's quickly talk about binary fractions. So because we covered that, the basic fractions, but what about more complicated fractions? Let's just say that if I have a value, let's just say 1, 1, 1, 1, and oh, hold on a second. Let me erase this. Let's just say that I have a number. Let's say 50 to 53, and let's do dot about okay. So if we were to convert that into binary, this side, hopefully this part's review, right? You just divide by 2. So 53 divided by 2, you keep the remainder. And this would be 53 divided by 2 will have a remainder, and it'll be 26. And then 26 divided by 2 will have no remainder, but it'll be 13. 13 divided by 2 will have a remainder, and it's 6 divided by 2. 3 divided by 2, and this will be 1 divided by 2 and 0. Okay, and this is from bottom up. So 53 is 110101. Okay, now for the fraction side, I think that we haven't talked about this before, so let me quickly show you how to do the fraction side. So the fraction side, you start off with just the fraction. And what you do is instead of dividing by 2, you multiply by the number base. All right. So you multiply by the number base. 0375 would be say 0.750. Okay, and then what you do is you just take just the fraction and you just keep multiplying the fraction by 2. And this would be 1.500. And then just the fraction, not the number in front. So 0.500 times 2. This will give you 1.000. And at this point, I can stop because all zeros at this point. So now, how do I get the binary? Instead of bottom up, now it's, oops, let me change the color ink. This will be top down. So this is 0.011. And this is what we want. Okay. So this number corresponds to this number. All right. Let's just do one more to make sure you know how to do this. Let's do, let's see, how about 17.25. So 17 would be 17 divided by 2, and that would have a remainder of 1, and this would be 8. 8 divided by 2 will be 4 with no remainder. 4 divided by 2 is going to be 2 with no remainder. 2 divided by 2 is 1 with no remainder, and then this, okay, and from bottom up, this is 1.0001. And now from the fraction side, it's 0.25 times 2 will give you 0.50, and 0.5 times 2 will give you 1.00, and I can stop, right, because it's 0. And this is from bottom down, so this is 0, 1. Okay, and this is the answer. Okay, so with that being said, now comes the question of why BCD. Why is BCD good for representing fractions? Because you can represent fractions easily. So as an example here, or the exercise, want to encode 0.2 into unsigned binary. Okay, so using the method we just showed you, I'm going to try to encode 0.2 into binary. We keep multiplying by 2, right? This gives me 0.4. 0.4 times 2 would be 0.8. I just keep multiplying by 2. 0.8 times 2 is 1.6. 0.6 times 2 is 1.2. And 0.2 times 2 equals 0.4. So notice that this is repeated, right? So this is actually, the resulting answer is going to be 0011 repeated to infinity. All right, so 0.2 in decimal, it turns out that you can't represent it in binary, at least not accurately, because it's an approximation. It's like 1 divided by 3, it goes to infinity. So 0.2, you think, well, it's an even number, but it doesn't matter. It needs to be base 2. So 0.2, if you try to encode in binary, it'll be 0011 to infinity. So the farther and farther you are to infinity, the closer and closer you approximate to 0.2. So what happens if I just leave it as 0011? What's the value here? So this is 1/2, 1/4. So this is 0.125. And this value is 0.0625, right? So if we add it together, this is 0.1875. So notice that this, if I use 4 bits, I can't represent 0.2 in 4 bits. Using 4 bits, this is as close to 0.2 as I'm going to get. All right, so this is going to be an issue, especially if you're dealing with money, right? Because each time you encode 20 cents, you just lost like 1.25 cents, which is no good. So if we were to encode this in BCD, 20 cents, how would we do it? Assuming that we have an implied fixed point, it would be encoded as 0010, 0000, right? So this is 2 and this is 0, and I'm done because of the implied fixed point. Okay, so BCDs allow for exact representation of decimals as long as it's a fixed point. All right, let's come back. So again, can't do it with unsigned binary, but with BCD, you have an exact. So this is 20 cents in BCD. All right, so that's good, but what are the downsides? I think we touched on some of them earlier. Here's some more. Is that with BCD, because of the nature of how things are stored, it's not really a number base. Arithmetic is a little more difficult. Like, for example, if we were just using a regular binary and we added the top numbers, 9 plus 8, the answer should be 17. And if it's just binary, it is 17. But the problem is BCD is 4 bits. So using 4 bits, what's stored there in BCD is not 17, it's 11, right? 1 and 1. So with BCDs, you have what's something that's called a +6 correction. That means that when you add any two numbers, where the number is larger than 9, you have to add 6 to it to correct it. So what would adding 6 do? This would be 0, 1, 1, 0. If you add to that, the resulting number is, which is 17, which is correct. Okay, so why is it +6 and not something else? It has to do with this, right? Numbers 0 through 9, you have 10 digits here. And on the left is your corresponding BCD, right? So the issue is after 9, you circle back up to 0. But after 1001, the next number is 1010. And then you have 1011. And you have 6 more numbers before it cycles back up to here. Okay, so that's what the +6 correction is doing for you. It's to recognize the fact that BCDs using 4 bits has 16 unique values, whereas decimal only has 10. So each time you go after 9 in decimal, it goes right back to 0. But with BCD, after you have 9, you have to add 6 to it to go back to 0. So that's why I have a +6 correction. So anytime you do any addition, as long as the sum is larger than 9, you're going to have to add 6 to the answer. Okay, so that's why for BCD, you probably don't want to use it if you do a lot of arithmetic. So hence, going back to what we said before, that its origins of BCD were usually for applications like clocks, where there's not a whole lot of adding going on, it's just displaying. All right, so another downside of BCD, I think we touched on this, on top of range is also storage, right? Is that, look at the number 255. Given the number 255, I can store it into binary, and it takes exactly 8 bits. And this is 255. Now, if I were to store this in BCD over here, that was 255 in BCD. But the difference is it uses 50% more space to store the same value. So BCD is not a real great storage medium. If you are just using it for storage, there's better ways of doing it. Okay, remember, again, the compromise is storage versus speed, right? I can retrieve, looking on the right, 255 is very quick. I look at this, I know this is 2, this is 5, this is 5. Very fast conversion. However, it takes up 50% more space. On the left is binary encoding 255. However, to get the value, I have to do the number base, 1 plus 2 plus 4 plus 8 So more work is necessary to retrieve the value, but it's stored in 50% less space. So I'm able to store more, but in order to access it, I have more overhead involved. Okay. All right. So guys, any questions? Tonight's actually a really short class. Any questions about BCDs?
Could you go back one slide for a second?
Okay. This?
Yeah, thanks.
Did you have a question?
No, I just wanted to see.
Okay.
So you add 6 to the, I have a question, Biz. So you add 6 to the last BC
To
digit?
to the answer that's being added. If you add 2 numbers and it's larger than 9, you have to add 6 to it to get the correct answer.
Okay.
All right. Guys, any other questions?
Professor, I have a question after class.
Okay, so just hang out after class. All right, if there's no other questions, guys, tonight is one of the shortest classes of the semester, so enjoy it. And we will see you guys again on Thursday. All right, so for those of you who have questions, just hang out after class. And we'll go over whatever you
Someone's
want to
asking
ask.
about like the homework or / the worksheets.
Yeah, didn't we cover that in the last class? This is stuff that will be you will be submitting via quiz online
Is there a due date?
after the exam, which is at this rate, I think the exam is either next Thursday or the following. Did we give a date for that?
I'd like to get one.
If not, I think there's the character lecture and then there's a review. So tentatively, it's going to be on Thursday, next Thursday, the 3rd.
That's
So
the
mark
midterm?
your calendars. Your exam is going to be tentatively March 3rd.
That's the midterm?
Yes.
And it's just stuff we've gone over in class.
Yes.
Because I noticed that we went over a lot of problems where you tell us to do these problems and we take a break and we like all work on it. Is like that's sort of what we're gonna see. Like
Yeah, except a little harder. Yes.
okay, cool.